Shappee, right? That is an associate professor at the University of Hawaii Institute for Astronomy. For his beautiful life at Hawaii, he's the Hubble Carnegie Princeton Fellow, and famous for his work both in theoretical and observational astronomy. Is also a founding member of the very successful survey for Supernova. Welcome.
So today I'm going to tell you about the ASAS-SN survey, context for the other surveys that are currently in existence. I'm going to go through a couple of the new capabilities that transient surveys are have that can open up new areas of scientific inquiry. And then I'll end with talking about how ASAS is making our data more usefully public to the community, and looking forward to kind of what the next stage is for following up bright transients. So this talk is very modular, so please feel free to interrupt if I start to go over on this. First, I'll just talk about, just mention my group here. I won't be able to talk about all of their work today, so I apologize to those who wait. I'll just highlight a few people. So the grad students are on top. Michael Tucker just left and started as a fellow at OSU. Chris Oshal just left as a postdoc and went to Service professor there. Anna Payne and Aaron Doe. I'll talk a bit about Anna's work at the Call Lunch. Aaron Doe has worked on the largest infrared supernova survey in existence. I won't talk about that at all. But both of them are on the job market issue. So look up their applications. And then two of my RU students are extremely talented. So when you start to think of transient surveys, one of the things that I think comes to my mind is how we've become extremely efficient at discovering new transients. So just showing the number of supernova candidates as a function of time discovered, you can see it's basically an exponential. So we've become extremely efficient at identifying new candidate transients across the sky. And this is really thanks to basically a spreading of the large area surveys that are across the globe. So here I'm just showing you some of the major transient surveys that are currently in existence. And what you can see is ASAS-SN used to be the only one that was actually in both hemispheres, except earlier this year, ATLAS is now extended to the southern hemisphere. TESS and Gaia are also quite useful. I'll kind of quickly walk through both of these surveys right now and try to put them in context. Some way to think about the different, how all different surveys fit together. So ASAS-SN is made up of 5 different units, where each unit is, a unit is shown here. They're all fully robotic. On each unit, we have 4 telephoto lenses, the 14-centimeter lenses. You buy these are just Nikon lenses, same ones that you see on the side of every sporting event. They're about 4.5 degrees on the side, so 20 square degrees per camera, times 20, 40 square degrees total at a given time. One of the downsides of ASAS-SN is that we have pretty large pixels, so we have about 8 arcsecond pixels, all of that max about 1.8, which means if you are worried about blending, then you have to be. So if you care about some private star source that's going to be black and clean, then it's more challenging. Image extraction works extremely cleanly on ASAS-SN though. So as long as the crowding source, the thin source, isn't also varying, they're typically fine, except for the Poisson. Our limiting magnitude, we've been taking data since the end of 2011. And V-band, in 2017, we added 3 units to G, and then in 2018, we switched all of our units to G-band. And now our limiting magnitude is about 18.5 magnitudes on a typical night. And these findings combined give us enough sky coverage to basically higher visible sky every single night. Currently, we take 3 90-second tethered images. We're actually thinking about separating them, so we take them back to back right now. We're considering spreading them out over time, so we take 1 90-second exposure, half an hour later take another one, and half an hour later take another one. That gives us benefits for short time scale variability. It'll hurt us for M-dwarf flares, but I think we've done enough for M-dwarf flares. It'll help on basically near-Earth hazardous object detection, which we are planning on helping Atlas out with. And also will help for transients on the time scale of like an hour. It's like point north for buildings. Sure.
By the G-band.
It ends up being the most efficient because we're the cost of having such large pixels is that we're sky background limited, even though we're pretty bright. So the reason we switched from V to G is actually that gained us a whole magnitude. So just it's really, so you would not want it would be painful to do an ASAS unit in like a high or something because it's that. We've expanded to be a global team, but most of the members, all these members are ASAS members, many different institutions around the globe. One thing to keep in mind for the ASAS is that most of them are science members, so they basically originally to do a specific science case. And actually, really only 4 of us are actually running the survey. So it's myself, Tom Holloyne, Hubble Fellow at Observatories. So it's really just the 4 of us doing all of the day-to-day work. So a favorite ask. Okay, I'm going to quickly go through the other similar surveys. So Atlas now has 4 half-meter telescopes. They have here. Each unit has a wider field of view of ASAS-SN with smaller pixels, so their pixel scale is about half our size. Their limiting magnitude is about a magnitude. And if you guys are on Twitter, you probably have seen this image of the TARC mission. This is actually taken from Atlas. One thing to keep in mind for Atlas is that it's funded for planetary defense, which means they use non-standard filters if they're optimized their science case to basically find sea killers before they actually hit us. And that dictates many aspects of their survey. So almost always planetary defense will take precedent over strong. There's some capabilities. ZTF is another large competitor. This is the only single site ground-based survey I'll talk about here. They took the 40-inch Palomar, they plastered it with 16 6K by 6K large format CCD detectors to use the entire field of view. 40% of the time is public. They have their typical cadence is roughly 3 days for introductory link for the public survey. And they're currently funded until next year. And they go about another magnitude deeper than ASAS-SN, although the public survey, of course, and stars, their primary goal now is also planetary, similar to Atlas, also based in Hawaii. They pretty much all the science that you think about when you think about pan-stars comes about just from PS1. Recently, in the past year and a half, 2 years, PS2 has come online, so now it's doubled. Each one has the largest astronomical camera in use, and that will be the case until LSST comes online. The field of view of these are smaller, but it's much smaller pixel scale, so they go substantially deeper and go to basically. Gaia maybe is one that you don't actually typically think of as a transient survey. Of course, it's an astrometric mission, but it's actually been quite useful for transients which are subtly vary over long periods of time. So you can see the spanning on the bottom here. So it's very non-uniform, but the typical revisit time is somewhere between 2 and 4 weeks across the sky. And it doesn't go quite as deep. The transient alerts don't go quite as deep as pan-stars can go. Basically, ZTF. But there's a little bit of funny accounting here because they only announce transients to this brightness, even though their photometry is still roughly 3%. So that's the validity magnitude, it's like a 3 or 5 sigma detection for ZTF, but you can get very good photometry from Gaia on the transients that they alert all the way down. So think about things that change slowly, subtly over time, like large, long-term AGN variability, and Gaia can be quite useful. HAPI isn't currently in existence, but I should mention it. HAPI is at Las Campanas in Chile. It's a single site, but it's quite a unique design, where basically it's using 63 telescopes. These are smaller lenses than ASAS-SN, but I'll cover it, as the name implies, one pulse pi iridians at a time. So it'll only go down to about 14 magnitudes, substantially shallower than ASAS-SN, but it gets you 30-second cadence throughout the entire. So it'll be quite useful for very fast time scale breaks. Think the brightest camera bursts each year. It'll have a record of these.
I don't know if the answer is here, but that's the limiting thing.
So I actually took out slides for. So I think this 14th, I believe, is in 30 seconds. So I took out a couple of slides, which is also true for TESS, which I'll talk about in a second. But basically, when you think of the surveys like this, which are just continuously taking data, then there's a trade-off between the cadence that you care about units or you just stack up data. So you can pick your, not arbitrarily, but you can sort of pick your cadence, and then you can go. So this is only for these extremely fast ones. So you can stack a lot of languages. Or you could like stack a whole night if you want so much. The TESS survey is another exoplanet survey, like HAT, except this one is obviously in space. It covers about 1/19th of the sky at a time. The full frame images have gone from 30-minute cadence, 10-minute cadence, and then now, as of last month, it's 2-second cadence. TESS has a lot of systematics that you have to fight with, but the geometry is really so. I do a lot of work with the TESS transients, but I won't talk too much about them this talk. But it's very similar to HAPI, except it can go down. So I'm a metrics-based guy, so I really care about citation. So this just gives you a feel for the different surveys, if you can read it, for basically how many of the citations each survey gets per year. One thing to note, I think there's multiple things, is the field is growing. So any junior science audience, obviously transients plays a lead. The decadal survey also agreed with me on that assessment. The other thing to note is that ASAS-SN does quite well even compared to our larger aperture competition. I attribute it to multiple things. One of them is that we try to, the core goal of ASAS-SN is to make our data public as usefully as possible, as quick as possible to the community. I'll talk a little bit more about that at the end of this talk. And the last thing to note is I didn't actually include pan-stars on this plot. I was trying to do transient science or time domain science, and the static skies were pretty hard to separate. Static skies. So, and if I put pan-stars on this, everything else will look small. So, pan-stars is on stage. Successful survey. Finally, I'll just go through and just compare field of view. This is a typical plot that's shown to compare the telescopes. This part will be a little tongue-in-cheek, but I'll get to the point, I promise. So like ZTF shows this, but basically the field of view of LSST is obviously smaller, exposure time is quicker, and obviously the aperture is much larger. But if you just wanted to compare field of view, then we can kind of step through and update this plot and just add pan-stars, the second pan-stars unit to it. If you want to compare, put Atlas on the same plot, then this is what Atlas will look like with all 4 of its current cameras. ASAS-SN, this is a single camera. Of course, we have 20. And then you can add TESS to this plot. Well, that's not saying that HAPI is by far the best survey out of all of these. They all have their different strengths. But it just gives you an idea that there's some trade-off that you make between aperture, sky coverage, depth, all of these things are different trades. And all the different surveys kind of fit together in this one. So this is kind of the summary to take away. ASAS-SN, I should have put half on top of this, but it's not currently public yet. But ASAS-SN goes to about 18.5, cadence roughly daily, Atlas magnitude deeper, 2 days, ZTF magnitude deeper, 3 days, and stars magnitude and a half deeper, longer, and then TESS, you can kind of deliver, get to different depths depending on what how many images you want to combine, as was previously mentioned, and then of course Gaia is very slow but very precise for its slow changing. So with that, I'll just quickly ask if there's any more questions about the surveys themselves before I move on and I start to talk about a couple science cases that highlight the new capabilities of astronomy. So I think one of the major gains that we're seeing with this kind of proliferation of all these transit surveys is that we can start to actually do science where the very early time light curves can actually be applied. The early time light curves depends on the transient, but there's typically model signatures that you can only catch in the early time portions of the light curve, because by the time you get to maximum light, those signatures are washed out. So for type 1a, the peak is basically mostly it's the nickel balls and things with some intermediate mass elements on the surface. And the peak is when you can basically get the decay energy from nickel 56 of that nickel ball. But the very early times that you haven't had time for that nickel flux diffuse to the surface, so you can look for other signatures that might tell you about the progenitor system of that explosion. Now, type 1a supernovae are, of course, important for a wide range of cosmological tools, but it's kind of an embarrassing fact that we still are uncertain about their progenitors and what's actually causing these explosions. I think nature, I mean, it's not just the fact that we haven't been trying at this for decades. I think nature actually might be a little bit cruel here. It actually has multiple different progenitor systems, but I'm going to go through and talk about one way to approach this problem. So there's two different channels, kind of main broad channels for of one is could be. The first one is double degenerate. So you can have two white dwarfs that are brought together. They're either collide or merge. They can either merge through gravitational radiation, just have a closed binary, goes through binary evolution, and two stars are close enough that over time they can get rid of their energy and angular momentum and combine. These actually will be visible in LISA once we launch LISA. Another way that you can bring these two white dwarfs together is in three-body or high-order interaction. So some work that was done actually here by previous fellows here were basically to show that if you have a third body in the system, you can go through quasi-resonance. That interacts with gravitational radiation to either accelerate this merger process, or, and if the inclination is correct and the third body is eccentric, you can go for the eccentric quasi mechanism. You can actually have a direct head-on flip. So there's multiple different ways that you can bring the white dwarfs together. The details are going to be very difficult to kind of suss out through observations of supernovae, but there's different ways that we can approach this particular problem. One of the things here is that in the supernova itself, there's going to be very few observational hints left over because the companion is just so small. And if they collide and then explode, then basically all this has exploded. So the double degenerate will be very difficult. There basically will be very few signatures in the supernovae themselves. A competing model is if you have a single degenerate companion nearby. This was kind of the favorite model through the 90s and into 2000s. I would say it's now disfavored in most supernovae. But you can accrete material from a nearby companion that grows your mass to near the transitor mass, where you can then ignite carbon, actually explode your carbon oxygen white dwarf. The companion, there's many different models in this one as well. The companion can be anywhere from a subgiant to main sequence star to helium stars and red giants. One of the key things here is that now, if you have the single generator, there's multiple observational consequences. You can look for the non-efficient accretion onto the white dwarf, so you can look for nearby material. You can look for the interaction between the ejecta and the companion. You can look directly for the companion pre-explosion, although that would be difficult if you get lucky. We've looked in a couple of cases. But here you can actually look for signatures. So one of the interesting signatures is actually in a very early time light curves. Basically, we can start to probe what material might be nearby the explosion in the earliest stages. This is the best observed type 1a supernova to date, ASAS-SN 18BT, discovered by the ASAS-SN survey on the star. Unfortunately, actually, we just went to lunation, so it actually wasn't completely visible. It wasn't visible from the ground. It wasn't easily visible from the ground, so we discovered it somewhat late. But luckily, it happened to be in a K2 Kepler field at the time, and so this teal is actual data. That's not a model. That's actual data from the telescope. And so you can do things for this supernova you just can't do with other ones, or at least very few other ones. And so you can easily see, right, there's a kink in the early time light curve, so you can try to fit with a single power law, which is kind of been assumed for most supernovae before. You can see there's large residuals, and this is the data well. Even if you go to a double power law, there's still some residuals, but it does describe. So from the early time light curve, I would say there's clearly a second component to this light curve, and what's the nature of that second component, what's causing it, is no big question. I should also mention that other supernovae that we have similar data for, but not quite as good, don't necessarily always show this. So sometimes they show a single component, sometimes they don't. Sometimes it just smoothly around.
So I wonder if I could ask, when you're observing that spectrometry through a filter, and if the spectrum is evolving in interesting ways, then this is not the same thing as what the volumetric spectrum is.
That's a good point. Actually, the literature is kind of funnily confused here. The first supernova that we could get somewhat similar observations for was the supernova 2011 FE. And there, the rho is consistent with a t squared. And so everyone said, oh, it's fireball, which just means it's a constant temperature that grows with time. But the problem is that we know the temperature changes with time. So it just happened to be that you picked the filter. Well, it happened to be that you observed it in the correct filter, such that what happened to be t squared. So that's another thing to keep in mind too. Is of course, this is it's a broad filter, but still just a single filter. So the SED itself is certainly changing, which will predict itself in exactly how this runs. One good case of exactly that is that, so the model for shock interaction with companion, kind of the first, most popular model is currently still used, was done by Dan Kaysen. Basically, the ejecta goes out, strikes the companion, sets up a shock, and then if you're viewing angle, if you're viewing it from the correct angle, you can actually then see this shock interaction. I'll give you an additional blue flux at early time. That doesn't mean it's only blue, it's this thermal emission. So even in redder bands like Kepler, you should still expect to see a signature from this. But the best fit model basically still leaves large residuals. It's actually that much better than a single power law as far as the residuals go, even though you've added a bunch of degrees of freedom. And it's a little hard to see here, but the biggest problem is that it smoothly rises. You basically, for the shock interaction, you expect to see a strong interaction right off the bat and have your model rise. We just don't see that in the light curve. Maybe the models need to be refined more, but I would argue that this is probably not the best explanation for the supernova, given later time observations as well. So what is giving us this extra source of flux? It's still uncertain. But one possible explanation is the nickel distribution. So typically when we model a type 1a supernovae, it's all nickel in the center with some distribution that falls off with radius, such as the red here. But you can actually change the slope of this work that's mostly been led by Tony Puro for different supernovae. So you basically smooth out the nickel distribution, and then that will change the slope at which your supernova rise. Now, obviously, none of these are a good fit to this data. All I'm trying to show here is that given the models that currently exist, if you put some nickel further out in the light curve, like these pink curves, you can imagine that you can actually explain. It's not very satisfying because now I can basically, if you allow me to pick an arbitrary nickel distribution, I can produce not an arbitrary light curve, but you can produce a large variety. But it does show that this is a plausible, possible explanation. The nickel explanation is challenging for maximum light observations because then you're adding a bunch of opacity on the outside of the supernova, so it's not particularly a great explanation currently, but a lot of theoretical work is currently being done on this. Can you produce, if you put nickel near the outside, can you reproduce the maximum light spectrum enough to this not immediately glowing? And finally, another possibility is that you can have nearby material that isn't necessarily in a companion form. So the companion is a bound, right? There's it has to be Roche-Lev overflowing, so that sets its radius as a function of its sets the separation as a function of its radius. But you can have additional freedom if you basically put material nearby, like a wind, that the ejecta will then run into, and then you can create features in the early time. Most of the natural ways that you would imagine doing this don't actually explain the early time light curve either that well. Usually it's either there's too much density nearby, so you get kind of like a peak similar to the nearby companion, or you just you can't really explain this like 2-3 days portion. But I think this is one of the possibilities that we can investigate kind of going forward. And I think the real way to make progress is not just to look at a single object, because then you can have lots of just so stories, but to actually gain and produce a much larger sample that we can then test our models in. This is where TESS and ASAS-SN come in, really TESS. ASAS-SN 18TB, not BT, is the best observed 1A so far in TESS. It's not nearly as good as 18BT, but you can see here, this is just similar companion models, the Kaysen models. You see that the early time data is good enough to start to constrain something like a solar radius. It's not nearly as good, but you can actually start to constrain both the progenitor systems and the Supernova. Michael Fajna has already published the first 6 sectors from TESS in a 2020 paper, and has recently actually just went through and done a similar analysis for the first 50 sectors of TESS. So that's up until a couple months ago. There's 307 type 1A supernovae in this sample, but only 74 of them are really close enough and bright enough to be useful at these very early times when it's faint. Basically, what you can see is that you can constrain, using the Kaysen model, you can basically constrain the separation or effectively the radius of the companion. For the light curves, we see no strong signature of a nearby companion in any of these light curves. And basically, these are just ruling out, these are the limits that we can place, the distribution of the number of supernovae that we have, on the size of the companion that we can place. So, so at 99.9% confidence, we can say that we disfavor large nearby. There's basically no strong signatures of large 40 solar radii companions near one. They just don't exist. If you want to be a little bit less confident, to like 95%, then you can roll out 14 solar. The reason these are somewhat weaker than you might imagine is because you have to remember that the companion model has a viewing angle effect. So you have to average out over all the viewing angles. So you actually do need these large samples to start to make statistical statements like this. We'll move on to a different science case. So is there any questions about 1A before I move on?
How quickly can a larger, say, a spectrograph get on?
That's a great leading question for the end of my talk. Currently, usually it's all still kind of telephone your friends, or if you have time, so it's still a couple hours is typically kind of the fastest turnaround. The gravitational wave source was a particularly good example of how effective that could be. But I think I'll kind of, at the end of my talk today, I think we need to skip all of the human intervention for spectroscopic. So I think we need eye views with robotic 2-meter telescopes that will automatically trigger and get data. So now it's a couple hours to a day, depending on word of mouth and who's on a telescope. But I want this to be like 15 Another interesting kind of capability that we're now getting, and that will only accelerate, especially when we go to LSST and the Rubin Observatory, is to catch rare transients and then follow them up. One such example I'll talk about very briefly here is tidal disruption events. So these are when a star happens to wander too close to a supermassive black hole. The tidal forces overwhelm the self-gravity of the star. It gets ripped apart. Roughly half the material gets thrown out, but half the material stays bound. And then GR precession actually bends it, so it actually interacts with itself and then give you a transient. Now these are rare. The rate is roughly 1/100th that of type 1As. So you have to take a lot of spectra of type 1A supernova just to even identify one of these ones, to identify it relatively early. But with all the surveys, we're now being able to do this. There's lots of open questions in this field. Even simple questions like where is the emission that we see when we find an optical and UV coming from? So you create this tidal stream, it orbits and it intersects itself. The magical story is somehow this material then falls, loses its energy and momentum, falls onto the black hole. But this shock interaction itself gives you enough energy. You have enough energy budget in that shock interaction to power the optical and UV light curves that we see. There's some that show late time rebrightening, that maybe that's actually the formation of an accretion disk. How these correlate with the properties of the black hole are all questions that people are trying to address. Because if we do, then we can use these as probe of quiescent, otherwise quiescent black holes. So in the local universe, only about 1% of supermassive black holes are actively accreting. And if you want to probe the other 99%, then you have to have some way of actually illuminating those that population so you can study them. So if you can figure out how all this works, and then you can correlate that back to the properties of the black hole, then we have now an independent probe in the local universe of all those quiescent black holes. And finally, there's also stellar brevity that's strong. And exactly how that plays, all these parts play together, is still uncertain. But we're getting larger samples. So in like 2014, there was a handful of these. 2018, we had basically 8 well-studied optical UV TDs. And as of basically through 2020, we had a much larger sample. Thanks to surveys like ASAS, you can't really read these, but ASAS-SN has the majority, ZTF, Atlas, Gaia, OGLE, IPTF, and TESS, those all have examples themselves. So this is really a field where basically everything's coming together. And then with these samples, we can study them individually, which is fruitful, but similar to the 1As, we can then start to actually look for global properties that are shared between these tidal disruption events. And I'll just mention one example of this global property, which is if you fit the black, well, actually, it's easier to see. This is just the luminosity assuming a black body fit, mostly to SWIFT. These are UV bright sources, so you really need the UV to actually get a handle on the luminosity and the temperature. But when you do that for a larger sample, you can see that the intrinsically brighter TDEs, they seem to decay slower than the less luminous and fast ones. These are, this is kind of reminiscent of like a Phillips relation for type 1A supernovae. In fact, my student, Jason Hinkle, went through and characterized the peak luminosity and then basically how much in log the TDE light curve decays over 40 days. And what you can see is this trend emerges and after the publication of this work, additional TDEs that have been discovered still fall in this relationship. But basically the bright ones decay slower, the faint ones decay much faster. And this is clearly pointing to an underlying physics of how TDEs actually work. And so basically now we can go back to the theorists and basically tell them that if you want to explain what tidal disruption events actually look like, you must have to have at least some explanation for the relationship. I will note, since I know there's a lot of cosmologists here, don't use these for cosmology. Scatter's way larger than 1As, they're way rarer, there's no reason to use them.
May I ask how operationally you distinguish TDEs from supernovae?
So
you have to classify it, and what do you do?
Yeah, so spectroscopic classification helps, although, and Colin will actually say, given a particularly good example of when that failed us, this core collapse supernovae can, in low resolution spectra, can look somewhat similar to TDEs. if you don't pay attention. The UV flux is really kind of one of the distinguishing characteristics. I won't talk about this at all here, but kind of a broader question that we're still dealing with is that there's a whole sample now of ambiguous nuclear transients. That's a name that Jason and I came up with, where it kind of looks like an AGN, but kind of looks like a TDE. And a lot of those don't follow this relationship, but there's other, but you don't say that they're not a TDE just because they don't follow this relationship. There's other properties that make them not follow it. And I think there's also, I mean, I could give an entire colloquium just on trying to suss out the differences between like change in look AGN, like big outbursts where they actually change their Seifert type, ambiguous nuclear transients, typically where like these, it's actually like a good example, slide anymore. But TDEs typically have a smooth rise and a smooth decline. I'll show that in Poland. So there's ambiguous nuclear transients that have a smooth rise, smooth decline, but their X-ray properties don't look the same as other TDEs. They don't necessarily follow the Hinkel relationship. Often they have previous AGN activity in those hosts. So I think there's a lot of subtlety there of distinguishing exactly kind of, and this is a quickly growing class too of what all these kind of weird outbursts in the synchronous galaxies actually are. I think is funny.
Specific definition of what a TDE light curve is, or is it more subjective? You look at different things and try to put them in different buckets.
I think we're still in the butterfly collecting stage where we're getting a large enough sample that the definition is still a little bit fluid and different between different experts. And I think we're gonna, the field will start to come to this consensus is where we will start to have definitions now that we have large enough samples, but it's still in the kind of touchy-feely kind of stage where we're still trying to figure out what's what.
Any correlation between the brightness of decay rate and host properties? Because, I mean, two things that come to mind.
That's a really interesting question. So for the host galaxy properties themselves, all to keep them out. TDs are extremely overrepresented in host starburst galaxies, but there are examples that are in more normal galaxies as well. I think that's an interesting question. I'll say the black hole mass estimates that we have are probably too noisy to really start to answer this question, which I think is really what you want. Because it's a little bit circular now, because now what most people try to do is they try to use something like MOSFET, which is some fitting code to fit the light curve of the TDE and infer what the black hole mass was. But we know that we're trying to correlate those two, so that's not necessarily the direction that I think you'd want other independent measurements of the black hole mass, which mostly are going to be galaxy correlations, which are quite noisy. So that you're to suss out kind of that you need a large sample. Errors in each individual mass measurement. It's also a direction that this field is definitely going.
Spatial positioning of the source?
That's also a good question. Depends on the source. We have UV spectra of a decent number of these now from HST. So there it's extremely good because you have the acquisition of HST. There would be like probably tens, maybe 100, tens of parsecs to 100, well, probably 100 parsecs. But for the majority of them from the ground-based resolution alone, it's consistent with the center, but then we always put like limits of like hundreds of parsecs.
Those that have good positional uncertainty, what do you find for them? What do they find?
They're all consistent with this.
Sorry?
They're all consistent with the very center. There's one weird example that's not. It's not clear. I think that's an ambiguous nuclear transport. But for all the other ones, they're very much.
You said they're overrepresented in post starbursts. Would you have been able to see them in starbursts, or?
That's a really interesting question. There's a lot of studies that have kind of gone into this. There's IR surveys that I think might help to start to address this. Is even I think Kirschley actually just had a paper from WISE seeing the WISE transients at the centers of galaxies that might be in starbursts, that might be the kind of the counterpart, the heavily extinguished counterpart to the tidal disruption events. But mostly the UV and the optical, where most of the emission is coming out. Typically, just else? Okay, I'm gonna skip. And then this might be, I'm biased obviously, but this might be the most interesting nuclear transient last decade. So how much, and I'll tell you about a potential repeating partial tidal structure. But I'm going to skip IceCube. Okay, so we're, I assume, looked at your Colloquium schedule a little bit, so I know you've heard about gravitational waves recently. But in 2017, the optical counterpart to gravitational waves kind of came to its full fruition with the GW 1708-17. You can see the LIGO and Virgo, LIGO detections here on the bottom. You can see the typical chirps. Two neutron stars coming together and merging. Perfectly with theory, basically just under 2 seconds later, we then had a short gamma ray burst. And it was a little bit weird for short gamma ray burst. It was low luminosity. There's lots of studies that have written on that since, but basically it was just an off-axis GRB. And so then the game was on after you saw this to actually try to find the kilonova counterparts. This is the optical emission expected from the stars. I was part of the two hemispheres, 1 meter collaboration. And I was actually on SWOPE the night before, and then I was on Magellan that night. And then when the alert came in, we just ended up searching for it. From SWOPE and both Magellan telescopes. This is just a little quick video showing the localization. And we ended up being very lucky here because it was very nearby and well localized from Fermi and from LIGO and Virgo. And it was only about 50 galaxies that really searched that were high probability. So very quickly, about 11 hours after the merger, we were able to go through with both Magellans. We had infrared optical, blue optical for one of the Magellans, and then SWOPE and I-band. And this is a color combination of the first images ever taken of gravitational wave counterpart. And so, of course, we announced this about 11 hours after merger. And really what this allowed us to do is kilonova evolve extremely rapidly. So on the course of hours, they change. On the left-hand side here, I show you basically stepping through time. And what you can see is that even the first day, it's evolving extremely quickly. On the right-hand side, these are the only spectra taken in the first 24 hours of this event, because we discovered it so rapidly, we could then turn around and follow it up. And you can actually see that the temperature is changing. And just from the black body radius, you can just immediately see that the ejecta is relatively stable. Now, there's huge numbers of papers. There's still multiple papers per week written on this event. I won't go through all of that here. But the thing I want to point out is that the rapid discovery of the counterpart was crucial to, especially to get the early time observations of this event. And it was discovered from SWOPE in Chile. This isn't at all, this is the Earth. But if LIGO had public announcements, and this was now, which LIGO does have public announcements, then we could have actually discovered it from South Africa about 4 hours earlier. Now, the left-hand side here, this is where the counterpart was actually found. This is the error circle from this particular event. And in the background, this is the ASAS-SN field coverage. So this is one exposure of ASAS-SN is one of these fields. And you can see that we would have prioritized this first field, and then 3 times 90 seconds later, we would have immediately discovered the counterpart quite bright. It was actually not the typical time. Many hours earlier from South Africa. And that could have then allowed us to basically get ready for the follow-up from South Africa, then also get ready just for follow-up, not for searching from the ship. And so that was 02. 03 finished, ended early because of the pandemic. And unfortunately in 03, we basically have no good counterparts. There's one that's been claimed, but I would strongly argue against that. You can ask me afterwards. So there's basically no good counterparts, even though obviously the optical transit community searched even harder. Basically, the nearest possible merger that had a neutron star in it was about 4 times farther away. It wasn't even a high probability than the original discovery. Here on the left-hand side is work from my postdoc on the Auger. And what it's showing is that for the 9 events that had a possible neutron star counterpart that was above 60% as given by LIGO, in 03, their visibility, the fraction of the probability region that was observable by ASAS-SN instantaneously over the first 24 hours. You don't need to look at the details, but what you can see is that basically like half or more than half at any given time is visible from the ASAS-SN network. That's because we're distributed in longitude. So if you're a single site survey, then basically there would always be a cutoff at some point in each of these where it's just no longer visible from you. And then also if it's another hemisphere, then you're kind of out. So the distributed network of ASAS-SN is a major advantage in doing these searches. This is one example right here where you can see that there's, most of the probability is basically going up to the North Pole, but there actually are a couple little spots in the probability region in the Southern Hemisphere at the same time. And we can get both of them and cover the whole thing right here. On the right-hand side, I'm showing you basically now the probability that was covered for all these different events as a function of time. And the X's are basically just the region where it's not visible from any assassination. So those are relatively small. And what you can see is that for a large number, we were able to get on them extremely fast. However, that's not always the case. One thing that when you think about this game is that we might become unlucky in the future. This particular event right here, which basically this is the sun, and it's basically right behind the sun. No ground mission observatory. So that's actually this red one right here with no. ASAS-SN in 03 was able to cover the most area of all of the alerts more than any other survey that's published. And I told you that we were pretty lucky in 02 to discover the Kilonova event because it happened to be nearby and bright. But one other thing to keep in mind, just like with PAT and TESS, is that you can stack. So this is, on the left-hand side here, I'm showing the limited magnitude of our reference images. So this is as faint as you can basically go in an individual part of the sky. Of course, the galactic plane is rough, but over the majority of this is something like 20th magnitude. So it's at least 1.5 magnitudes fainter than our typical limited magnitude. And on the right-hand side, it's basically just showing that the distance for an SSS-17A, the Kilonova-like event, what the detection limit of ASAS-SN is basically at different moon phases, and as a function of how long you want to sit on that field and exposed to the environment. And what you can see is that ASAS-SN can do a pretty good job out to about 3 to 4 times further away than the first one. So if the rate is reasonably high, then in 05, which is coming up in March, then we should be very well positioned to quickly identify the counterparts. Any quick questions on the gravitational wave? If not, I'll just want to quickly advertise one of the core goals of ASAS-SN, as I mentioned earlier, is to bring our data to the public as quickly and as usefully as possible. Over some parts of the sky, we have 8,000 images or more on fixed now at this point. Over the majority of the median field is something like 3,500 observations. In 2017, we released a pretty simple tool where you can just put an RA index into an online interface. And then behind the scenes, I would then run a forced aperture photometry pipeline to give you the light curve of an individual source. Now, this has been used a huge amount. You can see the citations as a function of time. It's cited more than 200 times this year alone, but there's many limitations to this tool. Namely, it takes about 10 minutes to give you a single light curve. And so to partially alleviate that, we're releasing variable star light curves. That's what Therendu has done before he became a Hubble Fellow at Berkeley. And additionally, he has an entire machine learning classifier that was trained from a citizen science project, Citizen ASAS-SN. We've had over 4,500 volunteers classify 1.2 million light curves. And then finally, the thing I really want to advertise is that in a couple of weeks, the paper will come out, but this is already live. So this is Sky Patrol V2. Here we're doing forced aperture photometry of 110 million sources in real time. So it'll go from data being taken to somebody be able to a point being added to a database for that particular light curve in about 30 minutes. And users can download 100,000 light curves in a couple. It's really mostly limited by bandwidth. This is work that was done by my former CS grad student, now engineer, Kyle Hart. It was a lot harder. There's a lot of technical details you can ask me after we're interested. But basically, it's the largest, to my knowledge, constantly updated and available database that's currently being used. So I'm sure Wilbur has a lot of them. Shortly will some. And finally, the last thing I'll go into is basically separating kind of the interesting new trends that you want to follow from all the others. So I showed you this black line at the very beginning of my talk, which feels like forever ago now. That's the discovery rate, but really all that these surveys do, including ASAS-SN, is just tell you that, hey, that part of the sky got a little bit brighter, or a little bit fainter at this time, like maybe you want to check it out. Really, spectroscopic follow-up is how you go from these detections to actual science. And as you can see here, our spectroscopic classification is just woefully not keeping pace with our discoveries. This is what the current spectroscopic classification looks like. ZTF has the SED machine on the Palomar 60-inch, which is a robotic telescope with a low resolution, small field of view IFU. That does the majority of it. This is actually at least three different telescopes in here, but the majority of them are from the SED machine. Actually, number two is actually my group, called the SCAT project that we have going at Hawaii, but this is all classically observed. This is me almost abusing my students. The number of nights I've had them observe, and I cannot ask them to observe it. To make this bar higher, I cannot do that class. What are we going to do? So I have an MRI from the National Science Foundation to roboticize the 88-inch. This is a venerable telescope on top of Mauna Kea. It's kind of the telescope that really put Mauna Kea on the map. Is at least one of the best sites, if not the best site in the world for optical and infrared astronomy. But it's a relatively old telescope, so there's lots of upgrades that we're currently doing. As part of this robotization effort, we're completely changing the TCS. We have to change the encoders. I won't bore you with all the details. One of the more interesting detail, though, is we replaced the tertiary mirror. Before it took basically a whole day to go from one instrument to another. There's three different ports that are now accessible, a through-cast and two bent-cast ports. But now we can go in about 15 seconds. We can switch between any of the three instruments on the telescope. And it's a well-instrumented telescope. On the near side, you see Roboreo. Roboreo 2 is being deployed right now, which will give HSC resolution imaging fully robotically from the ground. So it's very useful for finding basically how offset nuclear transients are from the center of the host, for example. On the through cast, we have a wide field of view, not ZTF wide, but a relatively wide field of view imager with multiple filters. And then the instrument that you can't see, but it's most interesting to me, is SNIFS, which is a small field of view IFU with a resolution of 12,000. This is perfect for getting large samples of supernovae or other transients that you want to follow up and actually even compare their properties. And it's extremely well calibrated. It can do better than 0.few% spectral photometry across this entire range, because the Supernova factory has been calibrating, has been really focusing on calibrating it over the past. So all those would be accessible. And then additionally, as part of SCAT, we started working with Katie Ackertel, a collaborator of mine from Australia. They have the ANU 2.3 meter, which also has a wider field of view IFU on board as well. So basically what we're pushing for, and it's also being roboticized. So then we'll have two telescopes on both hemispheres, or one in each hemisphere, with IFU, so that we can go through and actually start to make a substantial dent or a bigger dent in classification. I will note that we're still observing time limited. So even if we're getting a large amount of time on the 88-inch and sometime on the 2.3 meter, we're still going to go nowhere near the number of transients discovered. And this is going to be something that the challenge that the transit community must overcome. LSST, of course, as well, where it's a problem where we're going to have to go from small amounts of data to figure out the interesting science, and then use our spectroscopic resources very carefully and select them for home. This is a problem even for the bright transients. Then once you go to LSST, it becomes much more. With that, I'll ask if there's any questions.
you skip the neutrino, but I'm curious. So how often do you follow up? What criteria for you? No, I haven't seen the question. But want to follow up every.
So okay, for the IceCube, there's basically two different regimes. So this is just a model, well, it's actually data with models on top of it for what IceCube sees. It's a high energy neutrino detector at the South Pole. You can see at lower energies, you're basically just dominated by the atmosphere, as you know. These higher energy ones, though, you can actually have astrophysical sources that dominate over the atmosphere. So they publicly alert, IceCube does, since
Have gold, bronze, and but you probably
we follow them all up. The fastest we've gone from neutrino hitting the ice in Antarctica to on source open shutter Texas, I think was like 37 or 42 seconds. Around 40 seconds. We can go very quickly from to follow up.
Oh, okay, you try to follow.
Yeah, IceCube doesn't have that high of an alert, so that's interesting. I've been talking to Anna Frikolovich, who they want to start to push to lower energies by looking for, these are all individual neutrinos, but if you have two neutrinos at a lower energy, then perhaps that's a higher signal, but it's not that. So if they put that on alert stream, we'll follow that too. It's not that expensive for us.
What goes into that time budget you just mentioned? Is it that, is it IceCube's processing of the event? Was it you guys turning the telescope? What takes time there?
It takes us about 23 seconds to slew over most of the sky from our units. Stop and exposure, slew and take images. I think the other remaining of it, I think it was actually like transfer from the South Pole to Bolton. I think that was the majority.
You see opportunities for increasing the kind of basic ASAS-SN instrumentation. We highlighted at the end follow-up and classification.
Yeah, so the exact ASAS-SN design, I think ASAS-SN, Atlas, and ZTF, all of them will not be the exact, or advanced stars will not be the structure, the exact structure going forward for the bright and sky. I think there's two and a half main technological differences that are now coming to effect. One, CMOS detectors are very nice. Two, amateur grade telescopes and mounts have drastically improved, so they're actually reliable now. So I think you could basically get a whole bunch of 30-centimeter telescopes. And John Tyler and I have been talking about this a decent amount, and you could deploy them across the world. And the key there, which I think this is not an original idea for just us two, I think the thing that's often overlooked is that all of a sudden your enclosure becomes the dominant cost, and your computing becomes the dominant cost. So you have to be ruthless on every price. Every one of these, every cost item, if you want to, for a reasonable amount of money, have say like 100 or 200 30-centimeter telescopes, which are many different sizes. So I think it's the next logical step. Basically, just put them everywhere. And so John has this idea for basically fully self-contained solar power, batteries, Starlink. Everything is you put it in a shipping container, you drop it down. Then actually security might be the most expensive part. So maybe you just let some of them get vandalized. Drop them in really remote areas and just eat the fact that a few of them will be broken and stolen. I think that might be then if you really want to do this and you don't want to be, I like doing things smaller budget with a small team. I think that's probably the most reasonable plan. So I don't think, we're not gonna probably add more ASAS-SN units. Atlas won't add additional units that look like Atlas. ZTF you can't expand. There's a Schmidt in the south that Nugent, I know, is of course going to implement. So it's kind of like ZTF in the south, and not quite. I think that's kind of the end of those sorts of systems, and I think the next generation of systems, bigger than high, distributed, also still distributed. I think that's kind of the next step. It's not clear who's going to lead that next step.
We have past 1 hour, so if you have more questions, Ben will be here for the whole week. He'll be here at today here, and then tomorrow the university, and then Thursday here again, and then Friday university again. So please just come to well, let's thanks Ben for